And here we consider only the one interval, and it is your x1. Previously we have divided the whole domain to x1, x0, x2 up to xn, but here we consider only the one interval, and then we can generalize it for the n interval, no problem at all. Now corresponding to this, the coordinates of this point, if I call this as the point A, so the coordinates of the points A are x0 and y0. If I draw the tangent line at this point A going all the way like this, and we show it by say AL1. AL1 is the tangent line at the point A having coordinates x0 and y0. So the equation of this tangent line, which we have just written down, if you remember, so this is equals to y is equals to y0 plus x minus x0 times f of x0 and y0. So this is the equation of the tangent line at the point A. Now if you look at this tangent line, whenever it reaches to this line, it crosses at some place, and we call this, or we show this by the letter P, and the coordinates of this point P are x1, the x coordinate will be the same, but y will be slightly different, and we show this length from this point to this point, we show the length by y1 and 1, just to create a discrimination from the actual value. Now this point having coordinates x1 with y1, 1 is lying on this tangent line, so it must satisfy this equation. So here we can write down at x1, y1, 1, this equation takes the form y1, 1 is equals to y0 plus x1 minus x0 f of x0 and y0. So this is the equation after putting the coordinates of this point P into this equation, and we obtain this one. Now here, once again, come here, we draw a tangent line at this point P. Suppose this is the tangent line, and we show it by PL2. PL2 is the tangent line at the point P. Then slope of PL2 can be obtained as we obtain the slope of the tangent line AL1 by putting the coordinates into this equation. The same we can use these coordinates by putting them into here, we can obtain the slope of PL2. So the slope of PL2 will be dy or dx at the point having coordinates x1, y1 is equals to f of x1 and y1, 1. So this is the slope of the tangent line at the point P. After doing this, next we draw one more line, and the next line is the line that is going to be like that, and we call it as PM. And PM is a such line whose slope is the sum of the two slopes of AL1 and PL2. I repeat it. The line PM, this is the line which I am talking about. The PM is a line whose slope is the average of the slope of these two lines, in other words. Okay, so here we can write down the slope of PM is the average of the two slopes. The first slope is x0, y0, and the second slope is x1, y1, 1. So here you can see we have the line PM whose slope is this one. If we want to, okay, now we before going to some other direction, we can use this slope in order to construct another line. We are now going to draw another line through the point A and this is the line which we are going to assume is parallel to PM, and this we can label it the point B, and we can call it N. Okay, so B is having coordinates x1, y1. So A, B, and we take it ABQ. It looks nice. We'll take Q. ABQ is the line which is parallel to PM. Okay, and now this line ABQ is approximating this solution curve in order to obtain the y coordinate. I repeat it, we are going to approximate the solution curve by the line ABQ, which is parallel to PM, and to obtain the approximated value of the y coordinates y1. Now if we want to write the equation of this ABQ, so we have the slope, because this line is parallel to this one, so this line will be having this slope. If I use this point, then the equation would take the form, let me erase it from here. I am writing the equation of ABQ. The equation of ABQ will be y minus y0 will be equals to slope, this is your slope, in 1 by 2 times f of x0 y0 plus f of x1 and y11, and along with the x minus x0. Okay, so this is the equation of the line ABQ, which is approximating the solution curve, and we are approximating due to the reason we are looking for the value of y1. Now further, the point B having coordinates x1 y1 is lying on this line. So at this point of x1 and y1, the equation takes the form y1 minus y0 is equals to, if I write this first, it gives you x1 minus x0, and inside this will be 1 by 2 is there, I can take it here, this can be written like this, and inside this is f of x0 y0 plus f of x1 from here and y1 1 from the other coordinates. So this is the so far results we obtain. Now after writing this, we make a change in this result to obtain more compact form. So I'm going to erase all the material on the board, and I believe you have followed through all the steps. I once again repeated, first we draw AL1, then we place P on the line AL1 and we obtain the line which we have erased, and second we draw a line PL2, and this is the tangent line at this point P, and we obtain the slope of this tangent line at P, and then we draw one more line that is showing in between these two lines, and this line PM has a slope of the average of these two slopes, two line slope. Then we approximate the solution curve by the straight line, and we assume that this line is parallel to this one, and of course when these are parallel, so this one will be having the same slope, and we write down the equation of the line ABQ in this format. And next we place this point of x1 y1 into this equation, and we obtain the results of this one. So after doing this, the important thing which we, okay, let's see, we have already written down a result we shall be using later. Let's see what it is. Okay, I just shifted to here, plus f of x0 and x1 and y11 like this. So this is the so far result we obtained. Okay. Now further, if we simplify it, we get y1